Hi everyone and welcome back to the channel. Today we are going to discuss a circuit that combines a JFET and the BJT. We will see how the BJT acts as a constant current source to bias JFET, and we will calculate the key voltage VC and VD. If you consider the circuit, here emitter current IE is equal to the collector current of the BJT, and which is equal to the source current of the JPD, and which is approximately equal to the drain current ID. And here the gate current IC is approximately equal to 0. Let's take a look at the circuit. We got an N channel JPD and a NPN BJT and a few resistor. Notice how the BJT's emitter current essentially set the FPT's drain current. This is because the emitter current is mirrored as the collector current and directly connected to the source terminal of the FETs, which detects the drain current. This is called the constant current biasing, and it is really helpful technique for stabilizing the operating point of the JFET. Why it is important? JFET can have a wide variation in their parameter like IDSS and the VP. The constant current biasing helps us design circuits that are less sensitive to this variation. This provides us with the stable and the predictable circuit performance. Now to analyze this circuit, our first step is to simplify the biasing that are connected to the BJT's base. Since the JFET gate terminal draws practically no current, so that we can call IC is approximately equal to 0. We can ignore the 1 megaohm resistor during this simplification. First, we need to find the Thevenin's voltage at the node A. That we can consider as VTH, the just voltage divider output formed by the 92 kilo ohm resistor and the 33 kilo ohm resistor. So that VTH is equal to 33 kilo ohm into Vs, that is 10 volt divided by 92 kilo ohm plus 33 kilo ohm. That gives us 2.64 volt. Next, we will find the Thevenin's resistance. We can call it as RTH. This is the parallel combination of resistor R1 and R2. RTH is equal to R1 parallel to the R2, which is equal to 33 kilo ohm into 92 kilo ohm divided by 33 kilo ohm plus 92 kilo ohm, which gives us the equivalent resistor as 24.3 kilo ohm. With the Thevenin equivalent in place, we can now find the BJT's emitter current. It is IE. We will apply the Kirchhoff voltage law around the base emitter loop. By considering the base to emitter voltage drop in current BJT, we will consider VBE equal to 0.784 volt. Also, we know the relationship between base current IB and the emitter current IE is equal to beta plus 1 into IB, given that the beta is equal to 200 in this BJT. We can plug that into our KVL equation and solve the IE. 2.64 volt, 24.3 kilo ohm into IB minus 0.784 volt minus 1 kilo ohm into IE is equal to 0. When we rearrange this term, 2.64 volt minus 0.784 volt divided by 1 plus 24.3 divided by 201. It approximately equal to 1.65 milliamps. Great. We have our emitter current, which is also a FPT's drain current ID. Now we can easily find the voltage at drain VD. So that VD is equal to 10 volt minus 2.4 kilo ohm into ID, which is equal to 10 volt minus 1.65 milliamps into 2.4 kilo ohm. That comes out to 6.03 volt. Let's talk about how the JFET is operating. We know the ID, IDSS, which given as 0.5 milliamps, and Vp is equal to minus 6 volt. We can plug this value into the JFET's characteristics equation. This equation relates to the drain current to the gate to source voltage VGS. It is a fundamental equation for understanding JFET's behavior. In this case, by knowing the drain current and the JFET parameter, we can calculate what the VGS of the JFET will be in the circuit configuration. Finally, let's find the VC, the voltage at the BJT's collector, which is same as that of JFET's source voltage. First, by using the base current and Thevenin's equivalent calculated earlier, we can find the base voltage. And the base voltage VB is equal to 2.64 volt minus 24.3 kilo ohm into 1.65 milliamps divided by 201, which is equal to 2.44 volt. Since Ig is approximately equal to 0, then Vg is equal to Vb equal to 2.44 volt. Now that we know the gate voltage and the drain current, we can rearrange the JFET equation from earlier to solve the VGS. So the VGS is equal to 1 minus square root of ID divided by IDSS into Vp, and we will plug the value into our current equation. This is equal to 1 minus square root of 1.65 milliamps divided by IDSS 0.5 milliamps into minus 6 volt as a Vp. When we simplify this, we will get VGS equal to 4.92 volt. Since we know that VGS is equal to Vg minus Vs and Vc is equal to Vs. We can now solve for Vc. Vc is equal to Vs equal to Vg minus VGS. So which is equal to 2.44, 4.92 volt, and which is approximately equal to minus 2.48. We have successfully analyzed this JFET and BJT circuit, figured out the constant current biasing, and calculated the value of Vd and the Vc, and we found VDS 6.03 volt and VCS minus 2.48 volt. So let us verify in the simulation. So Thevenin's voltage VTH is approximately equal to 2.28 volt and collector current I is approximately equal to 1.4958 and voltage VD is equal to 6.445 volt and the voltage VB is equal to 2.28 volt and value of the VC will be 2.93 volt. So our theoretical calculation and the practically simulated values approximately matching each other. I hope this breakdown was helpful. If you enjoyed this video, please give a thumbs up, subscribe to the channel for more electronics tutorial and hit that notification bell so you don't miss any future content. Thank you for the watching. I will see you in the next video. Thank you.